All right, let's take a look at problem 3. To convince yourself that the entropy of a bath changes even though its temperature remains unchanged, consider the following case. A tub that contains water at 40 degrees C receives 100 kilojoules of heat. Calculate the final temperature of the water and its entropy change if the mass of the water in the tub is 1 kilogram, 10 kilograms, and 1,000 kilograms. Compare your result to the calculation of delta S is Q bath divided by T bath. Okay. Just trying to take it all in. Got it. So, what we're going to want to do is kind of see this in kind of two ways. So, one, our system is going to be defined as this tub. All right. So, our system is going to be defined as this tub of water, and it's going to receive 100 kilojoules of heat. So, the first thing I want to calculate is taking my tub to be my system. Okay, it's going to be exactly the same for all three cases. It's just the mass changes. I first need to calculate what's the change in temperature upon the addition of 100 kilojoules of heat. And then after we calculate the change in temperature, next we'll calculate the change in entropy for all three cases. Now my assumption is that as the mass of my tub increases, that change in temperature is going to decrease. And what we're trying to look for or get a sense for is, how big is my system, right? Once my system gets large enough and I can assume it's a bath, right? The assumption when we assume something's a bath is that the change in temperature is zero, right? And so what I would expect is as mass increases, the change in temperature, right, essentially goes to zero. And then what we want to show, though, for all three cases is even as the change in temperature goes to zero, as mass increases, that the change in entropy still is non-zero. Right? And then we're going to compare that to our calculation of assuming that our tub is a bath, where we just use that constant temperature of 40 degrees C and compare. Right? So cool. So the problem says, well, so it words it as, show that, even though for a bath the temperature remains unchanged, that the change in entropy isn't. But this is also good because we can get a sense for, how we're able to consider something is a bath, right? Once the temperature gets large enough, that change in temperature is going to be negligible. So again, I'm going to assume that my system, right, as I think about it in this case, my system is going to be my bathtub, right, which will eventually become our bath, right? But we're trying to take our that as our system and look at the effect of receiving 100 kilojoules of heat. Okay, so heat, right? So I'm going to receive 200 kilojoules or 100 kilojoules of heat. Okay, so that's going to be a positive Q. Okay, and I'm going to write as Q total. It's going to be a positive Q because it's heat received. And my initial temperature is 40 degrees C. And then we're going to analyze this process for three different cases of mass. Okay, and so this will be mass, and we'll evaluate all three individually. Okay. All right, now we're also told to assume that we have an isobaric process where Cp is equal to 4.18 kilojoules per kilogram Kelvin. All right, so how do we use this? Because the first thing I need to calculate is my change in T. Okay, so let's take this in a couple of steps. Okay. So we're told to assume we have an isobaric process. So for an isobaric process, recall that our first law energy balance reduces to delta H is equal to Q, where delta H is equal to the integral from my initial state to my final state, Cp dt, where if here we're assuming that Cp is constant, that's going to be a Cp times T2 minus T1. All right, so now in this problem, though, we're looking at extensive Q. Okay, so we're going to have that Q total, okay, which is known, is equal to, right, M times Q, which would be equal to M times CP times T2 minus T1. All right, where Q total, right, my total heat added is known. So my first question is, can I solve for T2, right? Can I solve for my final temperature? And I can, right? So let me expand. So this would be MCP T2 minus MCP T1. So I'll get that MCP T2 is equal to Q total plus MCP T1. So let's bring this over to the left-hand side. So T2 then is equal to, I'm going to write it as Q total divided by MCP, so divide by MCP plus T1, since MCP T1 over MCP is just T1. All right, so what I'll be able to do is for, all three masses, I can calculate T2. And then what I need to do is for all three cases, I also need to calculate delta S. Okay, and I'm going to compare that to the case of a bath. Okay, so I'm going to go over to a new page just because I'll work out all three cases up here. Okay. Now to get delta S, okay, the key is that delta S ds is equal to, okay, dq reversible over T. Okay, so we're not going to assume a bath here. Okay, we're not yet assuming a bath. So dq reversible, all right, we're told, what the value of Q is. Okay, so that'll be relevant for the bath case. But if I think of dq reversible here, okay, what I'm going to plug in is if I go back up to my first law of balance for an isobaric process, okay, in its differential form, all right, I would get the dq, so I'd get the dH, come on, stylus, is equal to dq, which in this case would be equal to Cp dt. Okay, so the differential of dq over t, well, is going to be Cp over T times dt. Okay. All right, so then my change in entropy, okay, so delta S, and I should note here, okay, that what I'm going to want is delta S total. Okay, so I'm going to want delta S total. Right. Well, okay, let me get delta S, and then let's get our equation for delta S total. So to get delta S then, okay, that's going to be equal to, come on, stylus, delta S is going to be equal to the integral from my initial state to my final state of ds, which is the integral from my initial state to my final state of Cp over T dt. Okay. Now in the problem, all right, we're given a value of Cp that's constant, so I'll bring it out and have the Cp times the integral from 1 to 2, 1 over T dt. So delta S then is equal to Cp times log of T2 over T1. All right, now I'm going to get the extensive entropy because that's what I ultimately want to compare to when we perform our calculation with our bath later on. So delta S total is going to be equal to M times Cp times log T2 over T1. All right, now let's compute all of this for case, I'll call this A, B, and C. Okay, so so let's do it. So what I'm going to do here is I've got a new script. So let's get it. So CP is 4.18. That's kilojoules per kilogram Kelvin. T1 is 40. That's 40 degrees C. So I'm going to go ahead and add 273.15 to it. And let me spit it out so that I can write down what T1 is up here as well. And actually, I want to change this up a little bit. I want to take this equation, and since I'm ultimately interested in T2 minus T1, let me just go ahead and calculate T2 minus T1. So I'm going to rewrite this as T2 minus T1. Right, which is essentially my delta T. That's going to be equal to Q total divided by MCP. Right, because what we're looking for is as mass increases, right, and here we can see it, right, if Q total is constant and CP is constant, as mass increases, this difference is going to decrease, right, until the mass goes to infinity, in which case that difference goes to zero. So let me leave it as that so that we can calculate, and I'll call it delta T for all three cases. Okay, that way I'm not worried about the units and converting from Kelvin to degree C and what effect that has on that difference. Okay, so there's T1. I'll convert it to Kelvin, and then Q total is in kilojoules. That's perfect because CP is kilojoules per kilogram Kelvin. So Q total is 100. And that should be all. Okay. And then let me write our three masses. So mass for case A is 1 kilogram. Case B is 10 kilograms. And case C is 1,000. Okay, so I change in temperature, and I'll just label them for each case. So delta T is Q total divided by M times CP. So MA times CP for case A. I'll just copy and paste it for case B. For case B. And for case C. All right, so as I run this, right, I find that as mass increases, that as mass increases, the change in temperature decreases. All right, so delta T, well, that's right. So delta T for case A is 23.92. Delta TB is 2.39. And case C is 0.0239. Right. Okay, cool. All right, so if you wanted to, you could readily compute this as a function of mass, right? And what we find is as mass increases, delta T decreases. All right, it's an inverse relationship. And the limit of the mass goes to infinity, delta T goes to 0. All right, and so we're assuming when we have a bath that we have some massive reservoir so that the change in temperature is negligible. Okay, cool. Now let's also calculate delta S for all three cases. And so here we're going to need to make sure we're using absolute units. And so, okay, now is my bad. So T2, my final temperature. All right, T2, I can write as T1 plus delta T. Okay, So let me go ahead and let me compute T2 for, well, yeah, let me just go T2 for case A is going to be T1 plus dTA, just because I need that temperature for my calculation of S. And then case C. Okay, so then I'm going to get entropy. For case A, it's going to be M. So M for case A times CP times log T2 for each case divided by T1. And then I'll copy and paste this 3 times and just update B and C, mass in B and C, and then that final temperature for case B and C. Okay, so if I run it, right, change in entropy is, so 0.3077, 0.3181, and 0.3193, right? So it looks like it's approaching, right, a constant value. So let me go ahead and write this down. So I'm going to write delta S total for case A, so 0.3077, and that's kilojoules per Kelvin, right? It's extensive. For my second mass, it is 0.3181. Kilojoules per Kelvin. And for case C, it's 0.3193. 0.3193, and that is kilojoules per Kelvin. Okay, now we're asked to compare to the case of assuming we have a bath, right? So let's imagine that we had some other, maybe put a hot object that released 100 kilojoules of heat to my bathtub, right? So in that case, I'd take the bathtub to be, some bath. And so if we wanted to calculate the change in entropy for my bath, right? And so that change in entropy, we're looking at the extensive entropy, is going to be equal to, so that'd be Q the bath. Okay. Now when I talk about, Q of my bath, right? So here we're told that we're, the bath is receiving 100 kilojoules of heat, right? That's going to be extensive, right? Because typically we're going to calculate it from the calculation on the system. Right? And we know the, say, mass of my system or moles of my system, but not in this reservoir, which is infinite. So you have Q bath over the temperature of my bath, okay, which in this case will just be this 100 kilojoules divided by the temperature of my bath, which is our 40 degrees C, plus 273.15 Kelvin. All right, because we're going to put this in absolute units. So delta S bath, okay, and I'm putting a total on there just to remind myself that it's extensive, would be, so D, so be Q total divided by T bath is just T1. So if I assume the bath, then I get the change in entropy of my bath is 0.3193, which agrees exactly within 4 digits to the change in entropy for case C, okay, for which we had a change in temperature of 0.0239 Kelvin. So for my bath, I get, using 4 decimal places, 0.3193. Okay, so as the problem lays out, right, this accomplishes two things, right? It shows us that even for a change in temperature of essentially zero, the change in entropy is not zero, right? So even though the change in temperature is zero or negligible, the change in entropy is not zero. This is also interesting too here because we see this case where as mass increases, right, the change in temperature decreases, right, to the point where if mass increases enough, we can just assume that we have some bath. The temperature change is negligible, and so lots of good things in this problem. Hope that helps.